Welcome all of you. Myself Professor Kaustubh Kapandi. I am with Professor Yatnesh Kadam. Today we are going to learn and demonstrate two-stage reciprocating air compressor. We also call it as multi-stage reciprocating air compressor. Actually there are two types of compressor, rotary compressor and reciprocating compressor. I will show you the rotary compressor. It is not included in our syllabus, so we are not going to study this, but it looks like this. Let's see what is this multi-stage reciprocating air compressor. It is reciprocating air compressor, means there is piston and cylinder arrangement. Piston will travel from TDC to BDC and BDC to TDC. So this way the reciprocating action will happen. So that's why we say it is reciprocating air compressor. It is two-stage. We are going to compress air in two stage. We are having low pressure cylinder and high pressure cylinder, that I will show you later. In low pressure cylinder we increase pressure, in high pressure cylinder again we are getting more and more pressure, more higher pressure value. What are the various applications of this air compressor? You are familiar with one application. When you go to fill air in vehicle tire, we are using this air compressor. For painting purpose, we use this air compressor. To actuate pneumatic actuators, we use this air compressor. Here you can see the various actuators. We use compressor to actuate these cylinders, various actuators. With the help of these valves, we actuate these cylinders. In industry, generally we use this air compressor. Also, you know one application regarding our engine. In air injection system, what we do? We use this air compressor. We use high pressure air to inject fuel in combustion chamber with high pressure. Now we will see the various parts of this air compressor. First of all, let's see the cylinders. Here you can see this is low pressure cylinder and this is high pressure cylinder. This cylinder bore diameter is 100 mm and the high pressure cylinder diameter is half of this, that is 50 mm. So here compression ratio is lower as compared to this high pressure cylinder. So what pressure we are here we are getting, that is low pressure, and here in high pressure cylinder we are getting high pressure because of higher compression ratio. Here swept volume is less, so we are getting high pressure here. Now you see the various fins are provided on this cylinder. These fins are provided for optimized cooling. The cooling is required. Why required? If there is overheating, the piston and cylinder will get seized because of overheating. But when we compress the air, ideally we compress it at isothermal process. So temperature should be constant, but there should not be any overheating. Okay, during the compression, the process should be isothermal process. If process will be isothermal, what isothermal efficiency we are getting, that also will be higher. What is isothermal efficiency? It is isothermal work done divided by actual work done. So isothermal work done in numerator. When we are getting higher isothermal work done, when compression will be isothermal, then we are getting higher isothermal work done and efficiency will be higher in that case. This is power consuming device. Unlike our engine, which is or heat engine, which is power producing device, we are getting power from the engine. On our vehicle, what engine we are having, that is power producing device. But this device is power consuming device. What output we are getting? The high pressure air, that is our output. Free air delivery, that air will be high pressure air. So that is our output. So, or we can in terms of work done, if you want to say isothermal work done. Okay, isothermal work done, that is our desired work done. But what actual work done we are getting, that is our output. Okay, so let's come to various parts. This is low pressure cylinder, this is high pressure cylinder. Various fins are provided. When piston will travel from BDC to TDC, the air will get compressed. Let's say pressure was 1 bar atmospheric, and because of compression the pressure is now 3 bar. After compression, in this low pressure cylinder, the pressure will increase, air pressure will increase from, let's say, 1 bar atmospheric to 3 bar. So we are getting air delivery of 3 bar pressure air. When pressure will increase or due to compression, we know we are getting heating effect. So because of that heating effect, the temperature of air will increase. We don't want to increase the temperature. Why? Because here for the compressor, the isothermal process is the ideal process. The compression should be isothermal. As I said before, if process will be isothermal, what isothermal work done we are getting, that will be higher. So that value is in numerator for efficiency. So efficiency also will be higher. So during compression, the air pressure will increase as well as temperature also will increase. So we have to dissipate some heat from this cylinder. So temperature will lower down. That's why we have provided here fins. After this low pressure cylinder, air will pass through this intermediate pipe and it will go to high pressure cylinder. This is high pressure cylinder. Bore diameter is 50 mm. Here bore diameter is 100 mm. So after compression, the high pressure and some temperature also will increase. That high temperature air will go to high pressure cylinder through this pipe. On this intermediate pipe, if you see, some fins are given. Intermediate fins are given. We call it as intercooler. Why we have provided this intercooler? When air will get compressed, its pressure will increase, but temperature also will increase. But we don't want to increase temperature, so we have to dissipate heat. So when we add that compressed air, when we induct that compressed air in this high pressure cylinder, we have to induct a good quality of air, good density air we have to induct in this high pressure cylinder. If these fins are not provided, the high pressure and high temperature air will get inducted during suction in this high pressure cylinder. So less air will get accommodated in this high pressure cylinder. The volume of this cylinder is, let's say, 125 cc. So definitely 125 cc air will get inducted, but its quality will be lower, its density will be lower. Why? Because it has high temperature air, the volume will be higher. So less density air will get inducted. We are not getting good quality of air in this cylinder or after delivery of this high pressure cylinder. In this high pressure cylinder, the air will get again compressed. Let's say the pressure was 3 bar, inlet pressure was 3 bar, and it will increase up to 7 bar. In a low pressure cylinder, 1 to 3. In a high pressure cylinder, again 3 to 7. Now we have got 7 bar pressure air after this high pressure cylinder. Now you see, when this high pressure cylinder will compress the air, again its pressure will increase, but temperature also will increase. What is our ideal process? Isothermal. So to ensure constant temperature, means we are trying to keep constant temperature. So again the after cooler is provided. It is types of fins only. These fins are provided, surface area increases, heat dissipation rate increases. That's why we have provided these fins. Okay. So after high pressure cylinder, air will pass through this after cooler and heat will get dissipate, temperature will lower down, pressure will remain as it is, and at high pressure 7 bar, let's say for example 7 bar, that high pressure air will be stored in this cylinder. We call it as receiver. The receiver size is 250 liter. Because of back pressure of this cylinder, see, when this high pressure cylinder inlet wall is open, there will be suction. At the time of suction, inlet wall is open, and when it will get compressed, the both walls are closed, then exhaust valve will get open after compression, and that high pressure air will get received or will get added to this receiver. So because of back pressure of this reciprocating action, we are getting this high pressure air. So we stored it in receiver. How to measure that air delivered pressure? So we have provided one pressure gauge here. As the pressure will be higher than desired limit, there will be chances of accident. This cylinder can get burst. So to ensure the safety, we have provided one spring-loaded safety valve. So this is spring-loaded safety valve. Also, when pressure is 7 bar or 8 bar, that is our desired pressure. Let's say 8 bar is the desired pressure. So at 8 bar, the motor will get cut off. So we have used this device. It is called as pressure switch. So when pressure will be 8 bar, the motor action will get switch off and our compressor will switch off, and no further the pressure will increase, and it will ensure the safety of our device. But if pressure will decrease below 8 bar, if it is 7 bar, 6 bar, again the pressure switch will on the machine and reciprocating action will start. Again the pressure will increase up to 8 bar. Again if it is reached at 8 bar, again it will get cut off. So this way the device works.
So this pressure switch is there to keep the pressure of the tank constant. As Kapati sir explained, when we compress air and it is stored in receiver, the pressure will continue to rise because it is admitting mass of air into the receiver. So your tank volume is fixed, receiver volume is fixed. So if you go on adding more and more air, its pressure will start increasing. Once it reaches 7 bar, which is the set pressure, the cutoff switch will activate and it will stop the supply of electricity to the electric motor. As we go on consuming air to the tank or receiver, the pressure will start to decrease, and once it falls below its set limit, that is, it is, I think for this compressor we have set it to 5 bar. 7 bar. So for I think for this compressor this is set to 7 bar. So when the pressure reaches to 7 bar, the cutoff switch will again reactivate the electric motor and it will start pumping the air into the receiver again. So here there are a number of safety measures which are incorporated. First, as sir explained, this is the spring loaded safety valves. It will activate at around 10 bar, so it will prevent the pressure from increasing above 10 bar. You can change the pressure value by changing the spring force. Next, at the intercooler, again we have one spring loaded safety valve. So this prevents damage to the intercooler in case of blockage of air or blockage of valves. Now let us see how we are going to perform the trial. At various points we have incorporated thermocouples which will measure the temperature at the various points of the compressor. So these points are T1, that is the temperature before suction. So if you can see, the T1 is the temperature before suction. So that is the ambient temperature. T2, the thermocouple is placed here. It's suspended in air. T2 is the temperature after the first stage. So that thermocouple is over here. T3 is temperature after the intercooler. So that thermocouple is over here. T4 is the temperature after second stage. So that thermocouple is placed over here. And T5 is temperature of air tank. So that thermocouple is suspended in the air tank. So what we do is we start the compressor by giving the supply to the DOL starter. The motor turns and it turns that pulley. The speed of the motor is 40 rpm. It is a 3-phase synchronous motor. So this will cause the pistons to reciprocate. The speed of the compressor is half. The pulley diameters are half. So if you see the left side pulley, it is smaller pulley. The right side pulley is the larger pulley. The diameter is diameter of driving pulley is half of the driven pulley. So this speed is around 720 rpm. Okay. Speed of compressor is around 720 rpm. As the air is sucked into the compressor, it is sucked in through this air box. It is used to measure the volume flow rate of air. It has an orifice plate at the top, through which we use the diameter of which is used to measure the volume flow rate of air. The pressure difference between the atmosphere and the air box helps us to calculate volume flow rate of air. And how we measure the pressure difference is through this manometer tube, water tube manometer. is there. So we measure the difference in level of water when the compressor is in operation, and we calculate the flow rate of air. So that is one observation. Next, we set the compressor pressure to a constant value by discharging air at a constant rate from this compressor. We make sure the discharge rate is maintained such that the pressure reading in this pressure gauge remains constant, so that the amount of air admitted into the receiver is equal to amount of air exiting the receiver. So that way the pressure of this receiver remains constant. And for particular set pressures, let's say that pressure limits are set to 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, we take different readings of temperature. So the temperature readings, as I had mentioned before, are T1 is temperature before suction, T2 is temperature after first stage, T3 is temperature after intercooler, T4 is temperature after second stage, and T5 is the temperature of air tank. We take measurements of those readings for a set pressures, that is 1 bar, 2 bar, 3 bar, 4 bar, and so on. And simultaneously we also measure the manometric height difference of water column to calculate the volume flow rate of air. Next, we have this energy meter which measures the energy consumption of this electric motor. We assume we know the electrical efficiency of this motor is around 0.9 or 90%. We measure the time taken for completion of 5 revolutions of this disc of this energy meter. There is a mark on that disc which is used to note the starting point, and from that we can calculate the amount of electricity consumed by this electric motor. We use all these values to perform calculations. We find out what is the work consumed or what is the energy consumed. We find out the isothermal efficiency, that is the actual work consumed, isothermal work required to compress that air to the set pressure, to the actual work consumed by the compressor, and we calculate the free air delivered. Okay. So we will see the sample calculations once we perform the trial. Okay. Now we will start the trial. Observe the temperature has changed. It is increasing. Here you can see, observe the manometer height difference. There is a height difference in the limbs of the manometer. The left part is atmospheric, the right part is connected to the air box through this tube. Here you can see the disc of that energy meter turning. If you observe, you will see a red mark which will be the start point for our time calculation, time measurement. See, this is the start point of our time measurement. So we set our stopwatch and we measure the time taken for 5 revolutions. The energy meter constant is given over here. Revolutions per kilowatt hour, that is 75. So for 1 kilowatt hour it will turn 75 times. If you observe now, the pressure is increasing slightly. So we will keep this constant at 1 bar. So how we do that? We allow the air to be discharged from this exit pipe to this wall. keep the pressure constant by allowing the discharge of air, and we will take the various readings from this temperature indicator. So this is temperature after second stage. You can see it is higher than the temperature after first stage. Temperature after first stage is 64 degrees centigrade. Temperature after second stage is 78 degrees centigrade. Ambient temperature is 29 degrees centigrade. So we take all these readings and use them for our calculations. This is the first sample reading for 1 bar. Now for taking the second reading, what we do is again, we close the valve and allow the pressure to increase to 2 bar. We have to make sure that the pressure remains constant. So we have to constantly check on the flow rate. Now I will be closing this valve. So if you observe, the pressure will start increasing.